This content is produced by Pass the CSLB, an independent audio-first study companion for busy California B general candidates. I build these lessons from official CSLB study guide topics and reputable source-backed California materials so you can study on the go. This is exam prep reinforcement, not legal, professional, engineering, or job-specific advice. Exam content is set by PSI and the CSLB and may change, so always verify current requirements against official CSLB materials. No exam outcome is guaranteed. Now let's get into it. The most important envelope decision often happens just before drywall. Once the wall is covered, a missing air barrier behind a tub, a loose bat, an unsealed attic hatch, or the wrong vapor retarder location becomes expensive to reach. The central principle is simple. The thermal envelope has to be continuous, and continuity depends on sequence. A good product installed too late in the wrong layer or with an open edge cannot do the job assigned to it. I think of the envelope as the boundary between conditioned space and everything outside that conditioned space. That outside may be outdoor air, an attic, a crawl space, or another unconditioned area. Insulation slows heat flow across the boundary. The air barrier limits air moving through it. A vapor retarder limits water vapor moving through materials by diffusion. A water-resistive barrier manages bulk rain at the exterior. Those roles overlap in some products, but the roles are not interchangeable. That distinction matters because the repair has to match the movement. If air is leaking through an unsealed hatch, adding a low permeability finish somewhere else does not seal the leak. If rain is getting behind cladding, more cavity insulation does not create drainage. If a climate-specific vapor retarder is required, a sheet full of unsealed penetrations may still limit diffusion through the sheet, but it is not automatically a continuous air barrier. I want the function name before the product is chosen. The easiest confusion to eliminate is the difference among insulation, an air barrier, a vapor retarder, and a water-resistive barrier. The comparison chart separates those four jobs. Insulation slows heat transfer. An air barrier stops bulk air movement through connected leaks. A vapor retarder limits water vapor diffusion. A water-resistive barrier sheds bulk liquid water at the exterior and is installed so water drains outward rather than behind the layers below it. Think about a windy day. A draft through a receptacle opening is bulk air movement. That moving air can carry heat and moisture with it. Vapor diffusion is different. It is water vapor moving through a material, even when there is no felt draft. Rain behind siding is different again. It is bulk liquid water. One word, moisture, can hide 3 different transport paths, and that is why vague instructions create bad field decisions. The practical move is to trace each control layer all the way around the conditioned space. Where does it run at the wall to roof connection? What happens behind a one-piece tub? How does it continue at the attic access? Where do window and door openings interrupt it? A layer that looks perfect in the middle of a wall can still fail as a system at its edges and penetrations. I also separate continuity from thickness. Thick insulation can still have a bypass. A durable sheet can still have an open seam. A correctly classified vapor retarder can still be on the wrong side of the assembly. Product labels matter, but field continuity decides whether the installed system matches the approved design. Quality insulation installation makes that continuity visible by treating each insulated cavity like a 6-sided box. The insulation needs full contact with an air barrier at the top, bottom, both sides, interior face, and exterior face. A void between the bat and one face leaves room for air to circulate around the insulation. The insulation may still be in the stud bay, but it is no longer controlling the entire cavity as intended. The most useful supervision example is an exterior wall behind a fiberglass tub, shower, or fireplace enclosure. Once that large unit is placed, the backside may be inaccessible. The solid air barrier belongs there first, sealed to the framing before the fixture blocks access. If the sequence is reversed, the later choices are bad choices. Accept a concealed break, or remove work that was already installed. The missing step may be inexpensive before placement and costly after placement. Imagine a contractor who sees the tub delivery arrive early and lets the plumbing crew set it against open exterior studs. The insulation crew later reaches every visible cavity, and the wall looks nearly complete. The hidden bay behind the tub still lacks its interior air barrier. Covering the nearby framing does not repair that hidden opening. The correct field decision is to pause before placement, complete, and seal the inaccessible boundary, and only then release the next trade. That is the central learning loop for this episode. Continuity is the principle. Air moving around or through the intended layer is the consequence. Trade sequencing is the field choice. The memory connection is the six-sided box. Before an assembly becomes inaccessible, ask whether every side of that box already exists. The same logic applies at an attic access. California energy requirements call for insulation to be permanently attached to the access door with adhesive or mechanical fasteners. The access also has to be gasketed against air leakage. A loose piece of insulation laid over the opening can shift when someone enters the attic. An insulated hatch without a gasket still leaves an air path around the perimeter. The hatch needs both thermal control and air control. When project compliance documents call for quality insulation installation verification, the sequence has another hold point. Do not let drywall or another finish conceal the work before the required field verification is complete. I treat that as a release decision, not as a last-minute inspection request. The crew needs to know the hold point before material and labor are scheduled. Vapor retarder awareness starts with a restraint. California does not use one blanket wall rule for every climate zone. The verified location depends on the assembly and the climate zone, and complicated moisture design belongs with the approved documents and qualified design professionals. The California placement chart shows two rules worth keeping separate. In every California climate zone, from climate zone 1 through climate zone 16, the earth floor of an unvented crawl space must be covered with a Class 1 or Class 2 vapor retarder. In climate zones 14 and 16, a Class 1 or Class 2 vapor retarder is required on the conditioned space side of insulation, and exterior walls, vented attics, and unvented attics that use air-permeable insulation. The phrase conditioned space side is more reliable than guessing interior or exterior from a sketch. It identifies the side facing the heated or cooled space. In the colder California zones named by the rule, placing the required layer on that side limits interior water vapor from diffusing deeper into the assembly toward colder materials. I do not turn that rule into universal instruction to add low permeability layers everywhere. An assembly has to retain an appropriate drying path, and product facings can change vapor performance. If the plans, energy documents, product data, and field condition do not agree, the general B decision is to stop and resolve the conflict with the responsible designer or authority before concealment. More layers are not automatically more protection. The crawl space rule answers a different moisture source. The exposed earth is the source, so the vapor retarder covers the earth floor of the unvented crawl space. This applies across all 16 California climate zones. The important distinctions are unvented crawl space, earth floor, and Class 1 or Class 2. Leaving out any of those conditions changes the statement. Thermal bridging is another continuity problem, but it concerns heat flow through framing. Cavity insulation sits between studs. The studs themselves cross from one face of the wall toward the other and conduct heat around the cavity insulation. Continuous insulation addresses that path by extending across the framing or by being integral to the opaque envelope surface, interrupted only by necessary fasteners and service openings. Continuous insulation does not merely mean that bats touch each other from bay to bay. The framing still interrupts those bats. Picture a winter jacket laid over the entire frame instead of separate patches placed only between ribs. The jacket idea is the memory aid. The exact material, thickness, attachment, fire protection, and water management still have to follow the approved assembly. Single-member window and door headers receive special attention in the quality installation criteria. For 2x4 framing, the header needs at least an R3 insulation layer. For other assemblies, the minimum is R5. That insulation is placed between the interior face of the header and the inside surface of the interior wall finish. The number belongs to the framing condition, so I remember the pair as smaller framing R3 and other assemblies R5. Foam plastic can be part of a high-performance envelope, but it also brings fire performance limits. The California Building Code generally limits the flame spread index of foam plastic insulation and foam plastic cores to no more than 75, and the smoke developed index to no more than 450, based on the reference test method. Those index limits do not replace the requirements shown in the approved assembly and product information. They are a screening fact, not permission to improvise an installation. At a slab on grade, the moisture control sequence is easy to remember if I stop picturing concrete as completely solid. Concrete contains pores that can draw liquid moisture. The verified California green building requirement uses a capillary break beneath a slab that requires a vapor retarder. The capillary break may be a 4-inch base of clean aggregate that is 1/2 inch or larger. The vapor retarder is placed above that aggregate in direct contact with the concrete. The order matters. Soil is below, clean aggregate creates the break. The vapor retarder is next, and the concrete is directly above it. Suppose a crew places the vapor retarder under the aggregate, because that position seems protected from foot traffic. That changes the required relationship. The aggregate would sit between the retarder and the slab, so the retarder would not be in direct contact with the concrete. The correct supervision response is to restore the specified layer order before the pour, when the correction is still visible and reachable. This is a useful connection between envelope work and concrete work. Moisture control does not begin at the wall. The conditioned building boundary also crosses floors, crawl spaces, roofs, openings, and access panels. General B coordination matters at each trade handoff because no single subcontractor sees every transition. On the exterior wall, the water-resistive barrier manages rain rather than interior vapor diffusion. The California Residential Code rule in the research uses at least number 15 asphalt felt, or an approved equivalent. It is applied horizontally with the upper layer lapping over the lower layer by at least 2 inches. Vertical joints lap at least 6 inches. The direction is as important as the dimension. Upper over lower follows the same drainage logic as shingles. Water running down the face stays on the exterior side of each lower course. Reversing that lap creates an edge that can direct water behind the layer. At vertical joints, the larger overlap gives continuity where one run ends and another begins. Openings still require coordination with the approved flashing details. A field crew should not treat the felt lap numbers as a complete window or door flashing design. The water-resistive barrier, flashing, and opening installation have to integrate so each upper drainage layer releases water onto the layer below. When a detail is unclear, I want it resolved while the opening and surrounding layers are still exposed. This is also where the jacket analogy needs care. A breathable exterior water control layer may stop liquid rain while allowing some vapor passage. A vapor retarder is classified by how strongly it limits vapor diffusion. Calling both layers plastic or paper tells me almost nothing about their actual function. I need the listed properties, approved detail, climate condition, and location in the assembly. The final pre-drywall pause is a short coordination check, not a new design exercise. The checklist on screen starts at inaccessible areas. Confirm that sealed solid air barriers are already behind tubs, showers, and fireplace enclosures. Confirm that insulation fills its intended cavity and remains in contact with the air barrier on all 6 sides. Check the special header insulation. Verify that attic access insulation is permanently attached and that the hatch is gasketed. Confirm the climate-specific vapor retarder requirement against the project documents. Outside, verify the water-resistive barrier, lap direction, and minimum overlaps before cladding hides them. I would add one project-specific line to that check. If the compliance documents require field verification, confirm that the verification is complete before releasing drywall. If a proposed foam plastic product or wall layer differs from the approved assembly, resolve it before installation. If a vapor control decision requires hygrothermal analysis, send it to the qualified specialist. Good supervision includes knowing when the verified rule ends and project-specific design begins. Here's the takeaway I want to stay with you. The envelope is not a collection of products. It is a continuous set of control layers crossing walls, floors, roofs, openings, and access points. Air control, vapor control, rain control, and thermal control solve different movements. The general B-field decision is to keep those functions distinct, then sequence the trades so every required layer is complete, inspectable, and connected before it disappears. I made an audio practice quiz for this specific episode. It is audio-based. The questions are read aloud, and you answer by tapping, which works well when you're studying while driving, working, or otherwise on the go. Go to the description below this video. You will see a link that says Pass the CSLB. Tap it. It will take you straight there. If anything in this lesson raised a question, comment below and I will read it. Subscribe so I can help you stay on track through every episode until you get your license. I know this process takes discipline, and I am here to keep the next step clear.